Okay, good morning everyone. My name is Matthias. I'm actually with the City University London, not with the Institute in Germany, but that's minor. I'll be talking about the force or pressure sensor using a combination of photonic crystal fibers. And I'd like to start with a kind of quote. Is it working? Okay, can you hear me? No? Can you hear me? Okay, I'll try to speak a bit louder then. Pressure is considered to be the second most physical parameter successfully addressed by optical fiber sensors according to Pina and co-workers. Common optical methods used to measure pressure are intensity-based, but they are, they have the downside that source drifts must be accounted for generally. Fiber Bragg ratings are a very prominent type of optical fiber sensor, but they are mainly used as strain sensors, not particularly sensitive to pressure. Now, interferometric methods are increasingly used to measure force or pressure, and this talk is focused on interferometric methods, or one method. Applications usually include gas pressure, hydrostatic pressure, and many applications in civil engineering, especially in structural health monitoring. Now, how do those interferometric methods work? You see here is a Photonic interferometer, a fiber-based interferometer type, which consists of a fiber loop. Now we have a source, a broadband source here, whose signal is split by a 50-50 coupler into both sides of a fiber loop, which means that the signals counter-propagate along the very same path, which makes it very insensitive to any environmental changes. If a highly birefringent fiber is inserted in the fiber loop, one can obtain an interference pattern that shifts as the birefringence changes, as I will show you later. Now here's an example of two screenshots of such interference patterns. Now the wavelength shifts with the birefringence, and the birefringence is dependent on temperature and strain or pressure. So if any of those parameters changes, the entire interference pattern shifts. So if you pick up one of those peaks and follow it as the interference pattern shifts, we can determine the pressure. Now, how can we make a standard fiber birefringent? Standard fibers are, well, if you want to use standard fibers, you need to deform the fiber core or the cladding in order to introduce a higher birefringence. But there are specially designed fiber types, like the Bow-Ti here and the Panda type. For the Panda type there is another image here. It includes stress-applying parts which along the fiber core, which change the propagation properties of the light in one axis, this axis. So when inserted in a fiber loop, one can obtain interference as we've seen earlier. Now the thing with these fibers is that they are very sensitive to pressure, to temperature. It's about minus 1.7 nanometers per degree, which is really highly sensitive. So why we're using photonic crystal fibers is their temperature sensitivity is much less in the sub-picometer range per degree, which is about 1,000 times less. Now, what are photonic crystal fibers? In contrast to the standard optical fibers, the cladding is formed by a structure of microholes, and the cladding material is exactly the same as the core material. That's the reason why it's less sensitive to temperature. And the other type of fiber that we just saw, the stress applying parts are made of a different material with different temperature expansion coefficient. So this is the high-bi version of the standard type, of this hexagonal standard type, which is suitable for pressure measurements. Now, due to its flexibility in design of photonic crystal fibers, there are many fibers that can be found in literature, not especially for pressure sensing, but for other applications, depending on what you want to do. Now, those are the fibers that we use in this investigation. There is this highly birefringent fiber. Now, the birefringence is at the very bottom here. It's about 1.5 times 10 to the minus 3. 2 low birefringent fibers from different suppliers. You see it's about 1,000 times less the birefringence value. What the effect of that is, I'll show you on a later slide. And we have another fiber type here that ranges somewhere between the highly birefringent and the low birefringent fibers. Now, this is the setup. As I said earlier, we combine different types of fibers. Why we do that will be clear later. So we basically have our Sagnac loop here, have one high-bi or one PCF, one photonic crystal fiber here, and another one here. So now the pressure is applied to one of those fibers. You can see that here in this screenshot here. And we have fiber rotators in order to examine the influence of the direction the force is applied from. Now, these are two interference pattern screenshots, one of a low birefringent fiber and one of a high birefringent fiber. You see that the highly birefringent fiber is much shorter, 0.4 meters in length. This is 9 meters in length. So the peak distance in that pattern depends on the birefringence of the fiber and its length. The lower the birefringence, the longer the fiber must be in order to obtain at least 1 or 2 dips in that interference pattern. So now, what we want to do is we want to use this type of fiber, as a pressure sensor, but it needs to be very long in order to generate that interference pattern. So what we want is, or what we do is, we use a highly birefringent fiber to generate that pattern, and we use this fiber as the sensitivity, as the sensing element. Why we do that, I will show you later. Actually, I'll show you right now. This is an image of the dependence of the orientation of the fiber, or in other words, the direction the force is applied from. We have the two standard hexagonal structures here, and we see one of them. We have the wavelength shift here, the interference pattern wavelength shift, and here the orientation of the fiber. Now we see that for that specifically designed fiber, as you can imagine, the sensitivity is not constant, and it even changes the sign versus the angle. This is the most sensitive axis. This is the most sensitive axis here, and this is the least sensitive axis. So now that is a bit unfortunate when using it as a real sensor, because we always have to make sure we sense at maximum sensitivity. So we can twist the fiber, which is a bit tedious work. What we want is a fiber that is always, or that whose sensitivity is not changing the sign and is pretty much constant. There are other structures that are pretty much round. We didn't have any of that fibers, but I hope it becomes clear why we're using a combination of fibers. So this is a graph of this strain sensitivities of different combinations. The first row of fibers here is the one that is not the sensing fiber, that's in the same loop, but there is no pressure applied on that fiber. It's applied on the second one. Now, where are we here? We see that when we use this fiber as well, those are the two main approaches that we are focusing on. because we use the highly birefringent fiber to generate that interference pattern, and we use this kind of fiber to measure the pressure. Well, the arrows are a bit misplaced actually here in this version. Well, this arrow goes up here. So this configuration is the most sensitive one, but it's not most preferable because the interference, the birefringence of this fiber is just medium. So we needed longer fiber in order to generate the interference pattern. So this combination is the best one. So in conclusion, I've shown you the 4 different types of photonic crystal fibers that we investigated, and I've shown you the advantage of high-bi PCFs over standard optical fibers because they are low sensitivity on temperature. It was shown that low birefringent fibers, photonic crystal fibers, can be used as force sensors at short length. If we would use them on their own at this short length, we wouldn't see any interference. And it was also shown that the dependence on the direction of the force is applied from can be reduced by combining photonic crystal fibers of suitable structure. I would like to acknowledge the European Cooperation in Science and Technology for supplying the fibers and support. That's all I have. Thank you very much for your attention.